Hello guys, KNOCKCAT this side. So today we will solve yet another problem on GFG, and that is grade 2 binary equivalent. So the question says that we need to convert gray code to its binary equivalent. So now given an integer number n, which is a decimal representation of a gray code, that means the n which we have is actually the decimal representation of some gray code. What we have to do, we have to find the binary equivalent of the gray code and return the decimal representation of the binary equivalent. That means now this is like actually this is some gray code to some other number. This number is actually a gray code to some other number. Now find the binary equivalent of the gray code. So we will find the binary equivalent of this gray code and return the decimal representation of the binary equivalent. This should be a binary sequence. This should be a binary sequence, and we need to give the decimal representation of this number. I know I have made a bit complex. Eventually, what they say that we are given a number n, which is actually the decimal representation of some gray code. This is unknown to us. So in the example, they gave us 4. So they gave us 4, which is the decimal representation of some gray code. So like 110, initially they were given us 110 and then they got 100, and since we have the decimal representation, we got 4. Now they say 4. This 4 is actually gray code of some other number. So now this n is actually gray code of some other number. So they say find the binary equivalent of the gray code. So we have to find the binary equivalent of this gray code. And this is 4 only because the 4 we get is actually some other numbers gray code. So this is actually our new gray code, and now we have to find the binary equivalent of this gray code and then the decimal representation. That means binary equivalent would be a sequence of 1 and 0. We need to find the decimal representation, and that's how the problem is actually turned down, that we need to find gray to binary equivalent. So this is the gray code with us, and we need to find its binary equivalent, and after that the decimal representation. So I think the problem is clear. This was a bit confusing from here and it took me also time, but after that I analyzed the test cases and figure out that this 100 is also someone's gray code, and that's why this n would be a number whose which is actually a gray code to us, and we need to find its binary sequence. And yes, if we have the binary sequence, we can get the decimal representation. I hope the problem statement is clear now. And now the things boil down to actually find the binary equivalent of this gray code, that is 4. So let's look to the some theory part first. So what is actually the gray code? So gray code is like fixing the first set bit, fixing the first set bit and make it as previous, and this would be our this will add to our answer. And in the other steps, what we have to do, we have to take XOR of previous and current bit and repeat these steps till end. This is a diagram I took from GFG only. So what they say, fix first set bit. So first set bit, if this is a gray code, the first set bit was 1, and make it as pref and add to our answer. So this will be a part of our answer. Then take XOR of previous and current bit. Now this bit that we have taken at last would be our pref, and the coming bits would be current. So now this would be current. And now we have to take XOR of this previous and current. XOR is bitwise XOR. If we have same bits, their XOR is always 0. So truth table for XOR is actually this. Let's say 1 0, 0 1, 1 1, and 0 0. So for different bits, the XOR is always 1, and for the same bits, the XOR is 0. So here we have 1 1. These are same. That means now we will get 0. At next time, this would be become our pref. This will become our pref, and the next bit would be our current. So 0 0, again they are same bits. We will again get 0. We are doing XOR of previous and current. This time again, this will be our previous, and this will be our current. 1 0, 1 0 is 1. We will actually get 1. Now this will be our previous. This will be our current. 1 0. Again we have different bits. We can say their XOR would be 1 only. We get 1. Again for next step, this would be our previous, and this would be our current. And 1 1, again we have same bits XOR, bitwise XOR is always 0, we get 0. For the next step, this would be our previous, but now we don't have any other bit. So 1 0 1 1 0 1 0 1 1 0 is the gray code, sorry, is the binary equivalent to the given gray code that we get. And the algorithm is pretty simple. We fix the first set bit and then we do the XOR of previous and current bit. So this is the same algorithm I have written here. Fix first set bit and make it as pref and add to answer. And now take XOR of previous and current bit and repeat these steps till end. I explained what is bitwise XOR, and if you understand till here, then the problem is now just implementation based. So before coming to the implementation, let me tell you the most important thing. If we have to check if some bit is set or not, so we actually use that if to find if the ith bit is set or not, we actually use this. Why I'm telling this? We all know that if we have a number, they all are a binary sequence represented. If we have an integer, we have a 32 bit. We have actually 32 bits to represent that number, and that ranges from 0 to 31. And overall, we have 32 bits. So if I have to figure out that, yes, if I have this number, and if I have to find out that is my this bit is set or not, is my this bit is set or not. So how we find it? We actually find using this set of logic that if n, so 1001 would be, I think, 0 1 2 3 8 9. So this is actually 9. So what we do, we say 9 and 1 left by I. 1 left by I means it is actually 1 is here. Okay. We say 1 left by I. So 0 1 2 3. It is actually 3. So we say shift 1 by 3 bits. So 1 bit, 2 bit, 3 bit. Our 1 will come here and rest will become 0. Our 1 will come here and rest will become 0. And then we do so 9 and we get this number. Using this syntax, we actually get 1000. And now if I do the AND of these two, we know we have 9 as 1001 and this will come out as 1000. And 1 1 will always be 1 because it is bitwise AND. So we will get 1. That means yes, because we got 1 here at this position, we will get 1, and this result would be 1000. That means greater than 0. This is not equal to 0 because we will get 1000. That is actually 8, and which is not equal to 0. That means we now have figured out that the ith bit is set. That the ith bit is set. Now you might be thinking that why I told you this thing, because this is the thing that I'm going to use in my logic. So since the algorithm says that we need to fix first set bit, that means in my code also, I would be iterating from, let's say, from 31 to 0, because I've already told you it's a sequence of 32 bits, and I'm iterating from the very last bit because I need to find the first set bit. And if I find the first set bit using this same logic, I would say, okay, I will add that to my answer. I will add that to my answer. That means 1 left by I. Why? Because if I have like 1001 and after that 1000, we know that this bit is set, and that means if this bit is set, this 1 would be part of our answer. This 1 would be part of our answer, and that means my answer would be 1000 already. Next time when they will find these two bits are set or not. So this is 0 and the number which will form is 100. These are not set. So this will not add to our answer. Next time I would be at 01. So the number which will form fixing for this bit would be 10, and 10 and 0 again this will give me 0. Since this is 0, that means this is not a third bit. And next time when I came at 1 and the number shifting 1 by 1 bits or like 0 bits, this would be 1 only, and 1 and 1 would give us 1. So overall, next time we these two comes 0 and the only time we have came 1 is here. So eventually this number will be forming 101 only. So what I said, this logic that through this I have now find my first set bit, because we need to find first set bit, and for the remaining set bits what we need to do, so this I have find this bit as set bit. So now I know my previous is equals to 1. Why? Because this bit is set, so previous is 1. And the upcoming steps, I had just have to check that is my next bit, the coming bit are set or not. So if this is set, if the upcoming bit is set, then I have to do the XOR of, so this one. I will check in the next step, are my upcoming bits are set or not. So this would be my current, this would be my current, and this would be my previous. Because if this bit is set, then current contains 1, otherwise current should be containing. So like if this is set, current contains 1, otherwise current contains 0. And now I would add it to my answer only if my previous XOR and current, previous XOR current is 1. Because if it is not 1, that means the answer that we need to add is 0. So it's 0 is same as left leaving it alone. So we do previous and current. If this part is set, I can actually say, okay, now you can XOR with my answer with this one left with by I, because this is also going to be the part of my answer. Same when I show you, because this 0 0 came and this came 1, so it would have become 1 0 1 till end. And since now we know that, okay, I have added to my answer. Next time, my current, this current would be my previous. What we did when we are doing the algorithm. So next time when we form this number, this became the previous. That's why now I can say my previous would be nothing but this priv XOR current, because next time I would be again calculating the current. So I think you have now get a gist of what I'm actually saying, and now how we will able to do this or implement this. I will show you in the code, but the two steps that need to be considered would be this: fixing first set bit, and after that taking the XOR of the coming bit and the upcoming bit. So let's come to the code part, and I will try to make you explain from the code itself. So let's take first an integer answer, because I would add to my answer. Now those all things make sense. Since we know that all numbers can be represented in a sequence, and that from 31 to 0 minus minus I. Now what I said, we need to find the first set bit, because at first set bit, for the first set bit, that first set bit will have to come, and after fixing this first set bit, then there would be XOR of these two, XOR of these two. So first we have to find the first set bit. So I'm finding. So for this, I'm actually having a bool variable. Let's say first set, and respect is 0. And after that, I also have a previous. Let's say it also is 0. Now I will check that is my this bit is set. So the same logic. If n and 1, shifting my I to that bit not equals to 0, same means it is not 0. Okay, I'm not checking not equal to 0, because that itself means that it is not 0. So if this is set, and we have not find our first set bit till now, so I can actually say, okay, answer would be equals to, because this would be the part of my answer. And now since now previous and first set bit would be 1, because now I have find first set bit also, and the previous for this is 1. Why? Because this bit is set. And continue, because this step we only need to perform one, because fixing step is only once, and the rest one is taking XOR. So next time I would say, okay, tell me my current. So current would be nothing but n, and if if this bit was set, if this bit is set, I will say make it as 1, otherwise make it as 0. The same thing that I was talking about few minutes earlier. If that is set, make it as 1, otherwise 0. Now if their XOR, if their bitwise XOR is 1, then only we will add their OR, that this 1 directed by I, to our answer. If their XOR is 1, and if not, we will do nothing. But the next time, my previous will get updated to current XOR priv, current XOR priv, and that's it. And then we can just say return answer. So let me run this, and let's figure it out. Okay, we are getting 7. So this is accepted code. And if you talk about time complexity, the time complexity for this approach would be order of 32, we can say, inverse. So let's say the time complexity would be order of 32, and the space complexity would be constant. How we have approached this problem, and time complexity of 32, space complexity order of 1, and this is the exact thing we need to achieve. The problem was a bit confusing at above, but ideally it was actually find the gray code to its binary equivalent. And we know the binary equivalent was forming through sequence of previous and current, and we form the number accordingly with one left by I doing. So this is the same thing. And I think I forgot to explain the test cases. Let's see, a very bad thing I have done. But eventually, when I explained this, I think that was also like understood, because what we have actually do was this only. So like, although it has to be explained earlier, but let's consider it all now also. So we have 4, and for 4 we know it is 100. So we need to find the gray code for this. So for this we fix 1, then this would be previous 10 will 1, then this would be previous 10 will 1. So this is how we get the gray code for this. And so like, previous and current would be representing these bits, and when I'm doing one left by I, and I'm actually or my this to answer, so we will able to form the binary or the decimal representation of those numbers. Although like, I explained this part here also, I didn't take the actual test cases, but I think this thing was clear in itself. So that's all about the code. I hope you able to understand the intuition why I come up with this approach, because this is more easier to visualize, that we are actually fixing from 31 to 0. This is more easier to visualize. This is more intuitive than dividing by 1, because I have also like, after doing the code, I also used to see that what code GFG came up, and they came up with this. This is actually doing the same thing, but this is not very intuitive. Like, this is actually hard to visualize that how they are actually doing is. But when I say that we are representing the number in a bit sequence from 31 to 0, it's more intuitive that if that current bit is set, then I have to check just that my previous and this current bit XOR should give 1 to that that current bit to be part of my answer. So this is more intuitive in terms of visualizing the number as a binary bit sequence. So that's all about the code. I hope you get to understand, because it's more about understanding, or rather than just keeping one liners. So that's all about the code. Thank you, and KNOCKCAT this side.